Assalamualaikum and very good morning to our lecturer and our fellow friend. We are from Group B, which is NURHAFIZA, Sofea Hani, and me, SITI NURHAFIZA. We will discuss about compound, which is copper hexacyanurate. Now we will move to the introduction of the compound. The compound consists of transition metal ion 2 bond to the cyanide ligand. The compound was the dark brown in color. Now we will move to method of synthesis. Potassium ferrate, potassium hexacyanidofferrate 3 aqueous solution was mixed with the copper chloride solution. After that, the mixer was irrigated with the high ultrasound radiation for about 50 minutes. The resulting solution was dealyzed to eliminate ion excess, and it's from a very stable brown colloidal solution. And then the powder that was obtained by the centrifugation was washing by water. After that, the remaining solution will be removed and the solid obtained will be dry at the low pressure and room temperature. After 5 minutes, the solid was washed again with water and then dry it with N2. Now we will move to point group determination by NURHAFIZA.
So for the point group determination, hexacyanurate 2 has an octahedral point group. So next slide. So here you can see all the elements in the symmetry operation for the hexacyanurate 2. It has identity, it has inversion center, and for the n-fold rotation, next slide. For the n-fold rotation, it has C2, C3, C4, and 62 prime for the n-fold rotation. The right diagram is here. We can see the improper rotation of S4 and S6, and also the mirror plane of the sigma H and sigma D. So next, okay, if you can see here, for the point group charge from the start, the molecule is not linear. It has Cn exists n more than 2. So does it have a center of inversion? So yes. Does it have a C5 axis? No, it is only exit at C4, so it has octahedral point group. So next, third type of ligand bonded. The crystal theory focus on the 5p orbital of the ligand arranged in the regular array around a transition metal. The dz square and dx minus y square orbital point directly at the 6 negative charge located on the xy side axis. The energy of an electron in these two orbital level will be greater than it will be of a spherical distribution of negative charge because of increased electrostatic repulsion. I will explain later. The other three d orbital, dsy, dsz, and dyz are oriented at the 45 angle to the coordinate axis. The energy of an electron of these three is lower than the spherical distribution of negative charge. So next slide. As you can see from the left, the EG orbital point directly to 6 negatively charged ligand. So therefore, the electrostatic between the metal and the ligand increase as they close to each other. For the right diagram, the T2G orbital, they point between the negatively charged ligand. Therefore, the energy decrease because it's not closely to each other. So next. For the ligand field theory, the orbitals lie along the bond axis. The two orbitals rise relatively high in energy. These are like anti-bonding levels. The xy, the xz, and dyz orbital lie between the bond axis. These two orbitals will change energy only a little. These orbitals are more like non-bonding orbital, and this orbital sometimes called T to this side of orbital. Next. Okay, Fe2 has a 2d6 for the N configuration. It has 6 valence electron. So we use Cn. It is strong field ligand. Therefore, it contributes low spin complex. The low spin, the orbital splitting energy is too high. The next electron must pair up in low orbital because the energy needed for the electron to go a higher energy level is larger. Therefore, it is remaining electron pair up in the lower energy levels. Next, I will pass to Sofia.
Okay. Now I will talk about the spectra related to the compound. Here in the diagram, it shows the FTIR, the UV vis, the VTC XES, and the XANES. But I will only focus on the FTIR and the UV vis. So this is the FTIR spectrum. We can see two peaks, but we will focus on the red peak, which is the FE2 plus species, where the CN stretch is found at the 2057.6 centimeter negative mark with number. So uh, why does the red peak is higher than the blue peak? This is because the difference in the metal ligand bonding interactions of the metal center and the ligands of each complex. So the high intensity says about the higher metal ligand bonding interactions. So now this is the UV vis spectra. The x-axis is stated in the electron volt values. So how are we going to know the wavelength uh, of this spectra is by converting it using this formula. Then the Fe2 plus spectrum, there are three main features. The first two, which is 3.67 and 4.71 electron volt, correspond to FeDD transitions, which is the transitions where the vibrations of electrons from lower to higher energy level that are mixed with the ligand S and P orbitals and the surrounding solvent orbitals. So these two are the interaction between the DD transitions and the transition between ligand S and P orbitals involving the solvent orbitals also. Then the highest one, which is 5.31 electron volt, is composed of the metal to ligand transitions, which is the highest one since the electron from the metal orbital have to be excited with a lot of energy to the non-bonding, the anti-bonding ligand orbitals. So that explains why it is at a higher intensity. Next is the magnetic properties. As FAZLINA has said, the D6 configuration of the Fe can be either low spin or high spin, but because of the cyanide ligands that are strong ligands, causes the crystal splitting energy to be higher than the apparent energy. Hence, all the electrons tend to pair up at the lower energy level, and when all the electrons are paired up, it is called as a diamagnetic. Next, I will give back to FAZLINA for the geometry.
So for the geometry for this molecule is symmetrically assigned by the 6 atom of Cn. It has distinct octahedral shape. Also, it has bond angle of 90 degree between the Cn and Cn side to side and 180 degree for the Cn opposite the Cn ligand opposite the ligand. So that's all for the geometry.
Next, we move to pizza for the applications.
Okay, now we will talk about application, which is the last part of the presentation. First application of the complex is film and bifilm modified electrode. It used in chemistry and material chemistry. It's also including the area of electroanalysis and also in sensing and electrocatalysis. This is study about ion exchange and electron transfer study and also research in chemical surface. The electrochemistry technique was used to the synthesis of film. Second Application as the complex use as cesium absorber because the cesium absorber capacity of CHCF2 was determined by best experiment as a function of cesium concentration. The distribution between the solution and solid was determined around 45 by around 25 by analyzing the former. The last one is capturing dissolved ammonia. This is used because the fast absorption kinetic and least impact and of coexisting sodium ion, which is abundant in environment of water. The pH used for constant absorption is just around 2 to 7. That's all about application, which is the last part for the presentation by us. Thank you.
Thank you.
Pasal referen tadi nak cakap juga ke?